Welcome to the introduction to bulk analysis, which means processing large numbers of measured spectra by optical fitting using many instances of our CODE or SCOUT software. The mechanism to use several instances at the same time is called MIPSS, multiple instances for parallel spectrum simulation. And I have published an introduction to MIPSS already in one of the previous videos about batch control operation. Here the mechanism is slightly different, and I called it bulk analysis. I will explain in a moment what that is. Suppose you have a measurement system that produces a large number of spectra in a relatively short time, for example by doing a one-dimensional scan on a traverse or a two-dimensional scan using an XY table or measuring a time sequence, and you want to be as quick as the data acquisition with your optical analysis. In that case, you can use the concept bulk analysis, which I will explain and demonstrate in this video. Bulk analysis is based on a separation of the measurement process and the data analysis. So the strategy is to decouple those processes. So the measurement system produces new measured spectra, and the first step is that the measurement system stores the spectra in a transfer folder as data files all the time. Whenever it does a measurement, it stores the spectrum in the transfer folder using a naming convention that enables the SCOUT and CODE programs to find out, let's say, the position on the sample and the sample ID, usually just by using the file names. In order to prepare the data analysis, for bulk analysis, you need a so-called bulk analysis folder. Must be somewhere on your computer, and it's a folder which holds a subfolder called analysis methods, and this folder contains special SCOUT or CODE methods which do spectral fitting. In addition to the normal ingredients for optical simulation and adjustments of models, you need to have a few mechanisms which must be there. For example, in the list of optical functions, you must have an item which is called the global bulk analysis number of fits to do, which returns the number of tasks that are still to be done by the analysis. I will explain later how we get this number. In addition, there must be, in the list of spectrometers, there must be a trigger object that refers to this function, basically the number of fits that are still to be done, and executes a script if there is a larger number, larger than 0. The script must call the line bulk analysis do one fit, which basically takes the first task to do a fit and does it. In order to inspect the fitting results later on, in case you have some doubts or you want to see some details, it is recommended to have a second script in these methods that call the routine bulk analysis command select and read results file. You don't have to have the script, but it's very practical to include that in your SCOUT or CODE method as well. Finally, it's also recommended, that's not a must, to have a view object of type automation button, which simply shows if the timer is the automation timer is active or not, if it's running or not. That's also sometimes practical to find out what's going wrong if something is going wrong. Okay, second part of the preparation is that you start a SCOUT or CODE managing instance. That's a CODE method that has a certain collection of scripts and other properties, which I will explain in a moment. And the most important part is it must have well, it must start a certain number of MIPSS servers, and that means a certain number of Scout or code programs that run in the background and that will do the fitting in parallel. So there's a strong connection between the managing instance here, which will not do any fitting by itself, and the fitting programs here by Ole automation. So that's a strong connection where this managing instance can call methods and get back values from those instances here. Okay, besides the generation of the MIPSS servers, there must be some script lines which set the bulk analysis folder and the bulk analysis transfer folder. These folders must be known to the server instances as well, so they must be transferred there by Ole automation. In addition, there must be scripts which let the user select the wanted analysis method. If you have an option to use several methods, the user must be able to pick the one of his choice, and the script also must copy this method to all the servers. There must be a few optical functions, one that retrieves the number of spectra in the transfer folder, and another one that returns the number of fits that are still to be done for the current sample. And usually there should be two triggers. One that starts the data transfer, that means that transfers the spectra, the measured spectra, to the sample folders. I will explain in a moment how that happens. And the second trigger should start a script when all the measurement tasks have been done, and the script should write the final report for the sample. Okay, that's the preparation. The work starts as soon as there are spectra in the transfer folder, pushed there by the measurement system, and the managing instance here counts a number of files larger than 0. Then what it does is it takes the files, it pushes the files to a sample folder. First it creates the sample folder. That means it has to find out the sample name and generate a folder with the same name, and then all the spectra are copied there. Within this folder, it also generates a subfolder which has the name of the sample method, which is going to be used to analyze the spectra. And within this folder, it generates small files which just indicate, okay, there's a task, there's a fit here that needs to be done. So for every spectrum that comes in, there will be this indicator file that means do a fit for this spectrum. Okay, then when it has done these file copying actions and creation actions, all the servers are informed that there is a new sample and that they should start their fitting work. The servers will do the following. They will read the task files here in the sample method folder. If they find one, they will pick it, they will remove it so that the other servers will not find it anymore. And then they will read the spectrum file from the sample folder, do the fit, and return the results of the fit in the sample method folder. So they will write small text files called result files that will contain the fit parameters that have been obtained for this spectrum. Of course here, I have shown only the activity of one server, but all the servers here do similar activities with different task files, but that's important at the same time, so they can run in parallel. When all the fits are done, there is no task file here left in the sample method folder, then the managing instance can write the final report. That means it collects all the results files and generates one file which contains all the fit parameters in, let's say, Excel format or CSV file format. So once this is done for one sample, the managing instance waits for a spectra of the next sample. Let's say the XY table moves on, or the sample has been changed. The XY table starts again for a new sample, and this way a new folder is produced. The same thing happens again and again and again. And if the data analysis is fast enough, that means if we have enough server instances doing the fits while the measurements are done, then data analysis will be always as quick as the measurement system. So there will be no files piling up here in the transfer folder, but they will be analyzed at a high rate, high enough so that no files are left in this folder. Okay, let's start a demo system so that I can show you in an example how this will look in a real application. Here is a Scout configuration that you maybe recognize again. I have discussed its development in the video about automation and scripts. What it does, basically, it simulates the spectral output of a traverse system. There is a sequence of timer actions, and it's basically it produces reflectance spectra of a nickel chromium oxide layer on glass for different positions on the traverse. Maybe the easiest way to explain it is to show what it does. Here, this command start the time sequence. Lets me select a spectral name. Let's call it T1, and then if the script runs, every second it changes the sample position and it produces a reflectance spectrum, modifying the thickness of the layer and the oxygen concentration or the oxygen content of the nickel chromium material in a predefined way. And the task later on will be to analyze these spectra as if they were measurements and to be as quick as this sequence here. One fit every second. That's the goal. Okay, so the measurements are saved. Actually, they are saved already in the transfer folder. Let me show you where that is. That's here on my system. That's this folder here. So we have 32 CSV files which contain the spectra. The bulk analysis folder, that's this one here, which I have explained before. Right now it just contains a few Scout configurations. I will not use all of them, but it contains the subfolder called analysis methods, and here are two different choices of fits. I will only use the first fit method here, which I have prepared for this problem. Okay, let's start let's start the instance, the managing instance of Scout. I use Scout for this. As I explained before, it's a Scout configuration which contains a certain number of scripts and triggers. And if I load it, it generates one instance, one server running in the background. For the moment, that will do for the explanation, and then later on I will do another run using more servers than just one. So actually we can show the server using this command here. Right now it's empty, so there is no method loaded at the moment. I have to select a method by clicking here on this script, nickel chromium oxide fit. If I select it, this method is loaded to the servers. Right now there's only one, but you can see here this is the server which has a method, and actually we can just do a test. If we import one of the measured spectra in the transfer folder, that was here. If we pick one of those spectra and we press start, it should be able to do the fit within a few seconds. Not all the fits are as quick as this one. Usually I have limited the time to 4 seconds, so every fit is finished after 4 seconds with guarantee. I have tested that. Okay, so we can use the command hide to hide the server. And now what we can do is start scanning the transfer folder. Now the managing instance here should realize, okay, there are a certain number of spectra, and it pushes the spectra to the sample folder, which is called T1. Actually, we can take a look at that folder. There's a folder T1 here, which contains CSV files and which contains a method folder which has the same name as the analysis method, and the method folder contains the small text files which just indicate, okay, this is the spectrum name that needs to be analyzed. And the single server is now pretty busy doing one fit after the other. It always takes one of the text files here, picks up the spectrum from the sample folder, does the fit, and returns the values in the result files here. Okay, the server should give here an overview on the number of fits which are still to be done. The server also shows what is the current sample, what is the method that is used, where is the transfer folder, and how many W.Theiss servers we have. In addition, it shows for each server what it does at the moment, and the view update here happens, I think, every second. So it's not well up to date by a millisecond, but every second we can get a new overview on how everything is going. The action scripts that are needed to build the whole solution are those 5 here, and I will not discuss them here. I have discussed the principle, so it's not necessary to go into too many details at the moment. This is just a demonstration of what you can get. Okay, so it's only a short time to wait for the final result when all the fits are done. Only 3 left. So within a few seconds we should be there. I have built in a mechanism that starts to write the report file as soon as the timer here is counting, I think, up to 10. So the report file should be written. There's also a command here, write report, which I can use for manual generation of the report file. But this is done automatically by this method. And what you can see here is the thickness versus traverse position and the oxidation state of the nickel chromium layer versus position. And you maybe remember I picked a sine wave for the variation of the thickness with position, and just a linear relation that goes from a more oxidic state to a more metallic state across the traverse. So pretty artificial, virtual, not realistic, I guess, in this case. But at least we can see all the results are here. But it took quite a while for this one server instance to do all the fitting, and we can now very easily speed it up by a factor of 4 on my 4-core machine, but maybe even a little bit more. I have 4 cores on my computer, but they also use hyperthreading. That means each core can run 2 threads at the same time. So what I will try, I will generate 8 servers that run in parallel. They will not be 8 times as fast, but maybe 6 times as fast as the solution that we have seen right now. If I load the configuration with 8 servers, it will take a while. Let's start this. Because Scout has, the managing instance has to start 7 more times the Scout program. And each start takes a few seconds. So we can see here how every instance is created. I have seen workstation computers which are much faster than my laptop, where this is also much faster. It takes 1 or 2 seconds for each program start only. But we are soon ready. Okay, I guess it loads also the methods already. So if we click on Show Servers, we see 8 instances. I see that on the right of my screen, which is a little bit larger than the video shows. Here's server number 1, this is server number 5, server number 8. Basically, they are all showing the same fitting situation. So we can hide the servers again. And so let's hope if we start a new sample, T2, that we will get a much faster fitting. Oh, I have to click on Start Scanning. Sorry, forgot this. So now you can see that several of the instances in the beginning, all 8 of them were working in parallel. Now only 6 or 7. Actually, we have enough computing power to keep up with the production of new spectra. And as soon as the last spectrum is measured, it will also be analyzed. So we can, with the 8 instances, we can keep up with the running production rather easily. Let's do that another time for T3. So we are producing new spectra, and as soon as they arrive, they are analyzed. You can see that some of the instances don't even get work, so they are fast enough to keep up with production. Okay, finally, when we have a result, it would be nice to watch also, or to inspect the results, how the fitting was done. And there's a command for that, a script command here, which is called inspect specific fit. And what it does, it shows the first server, which is this one here. And then we can pick a result file, or I will show the server soon. And we can pick a result file. Let's say the position is 450 here. RES means result file. We can pick that. And then the first instance will load the 450 millimeter spectrum, and it will show the fit as it was here. You can see it has a script called inspect fit result, and we can click that and load the result for position 150. We can load any of the fits that have been done. This one was the last one, 3250. and you can see the reconstruction of the fit as it was when the result file has been generated. Oh, I hope this demonstration was convincing and showed how we can use several instances working on the same problem so that we can be fast enough with our data analysis for production, which produces a large number of spectra in a short time. I have seen solutions with 32 instances at the same time. For that you need a real fast computer with a lot of memory, but it's possible and it's not so expensive anymore to buy computers of this kind. That's all for today. I thank you for your patience and watching this video. Bye bye.